Okay, so we have these instructions, and this is just an example of them. This is obviously an XOR. It's at W level, that's word level, so I think this is 8 bits. I don't know. These ones are at long size, which is, oh, I bet word is 16 bits. Does anyone know? This is 16 bits, so I suspect. It's probably B for byte, W for word. B is 8, word is 16. Long is 32, because it's a long word. And then Q, which is right here, that's quad word for being 4 times as long as a word, which is 4 times as long as 2 times of bytes, which is 8 bytes total, which is 64 bits, which is the U64. So this quad, that Q refers to quad, which means 64 bits. So we move a bunch of stuff around. Who cares about this? I don't know. I don't like whatever's going on here. Here's some obvious powers of 2 going on. Here's a 24, which is pretty interesting. But all of the stuff that's happening in here, we're calling a start internal. Like, there's weird stuff going on in the language. But really importantly, there's something not going on in the language. And that's what we showed with grep. So if I look for a rotate left, which I know is the correct instruction because I found it on this reference manual, right? So it's called a rotate left. I can't find a rotate left anywhere in this assembly command. There's a bunch of things called prolog end, right? But if I look up a much more common instruction, which is move, which takes a value in one register and puts it in another register or saves it to memory or something, right? I'm moving bits around. There's many moves, so I know I'm successfully finding assembly instructions. I know there's many assembly instructions in this assembly listing, but none of them are the very fast rotate left instruction, which is odd because I don't know how you can make it more obvious you want to rotate left than directly telling the language, I want to rotate left. So this is odd. This is an odd feature of how languages work, right? This should be one of the most straightforward pieces of code in the universe to compile into something, because I'm just going to move this value into a register. There should be a single move Q, right, that takes this and puts it somewhere, perhaps an RAX, right, which is the X register, right? And then there should just be an ROL right after it, and I don't know if I have an example of that. And, you know, perhaps I want to shift with carry, rotate with carry, I don't know. That doesn't make sense to me. But this is what it should look like. And here's a good visual representation of how it's expressed. But anyways, Rust C can't figure this out. And in fact, I'm pretty sure that if I write this in C, I don't know a way to get it to come out as a rotate either. I spent some number of hours on it last year trying to get GCC, which is this thing. I couldn't get it to produce rotate instructions either. I don't know how you get this stuff to produce rotate instructions. Now, on one computer, I can write code that commands the computer to literally use exactly a rotate instruction. But it only works on one computer, which defeats the purpose of having programming languages, right? So I haven't solved this problem, but I find it interesting. So anyways, however you want to solve rotate, do it. But be aware there's this like pretty serious lingering complexity going on behind the scenes, right? And there's not actually great solutions for how to do this, to my knowledge. Okay, does anyone have any questions about macros or rotates or anything else before we get into SHA? Is everyone having a good time so far this semester? Okay, that's good, because the good times are mandatory. Okay, so before I begin the SHA slides, I have to say something that I have never successfully communicated through slides, but often when I talk to humans one-on-one, I can communicate. The goal of SHA, SHA, the secure hash algorithm, is to make a small number that you generate from a file in a computer. That file can be an executable or something, right? And the goal is that any bit you change in the big file has an unpredictable effect on the small number. What this means is as we go through SHA and as we learn about the algorithm, what we're going to see is we're going to see a lot of bits being moved around and multiplied by each other and shifted relative to each other. That's so that every bit affects the value of every other bit at high probability, right? This is useful so that you can tell if something has been tampered with. And so it makes it very hard for someone to tamper with something and get the same small number that represents the big number. So for example, if I were to count up the number of ones in a file, it would be very easy to tamper with it in such a way that I keep the same number of ones. That would be too easy, right? So we have to do all of this other stuff. I don't know if that's going to make sense to you, but sometimes I hear, hey, like, I don't know why I was doing all this stuff. We're trying to make every bit affect the value of every other bit. That's all. And the reason we're doing that is so people can't lie. Because as we know, you're not allowed to just go on the internet and tell lies. Okay. Right. I don't know how SHA is going to go. So last year I taught this in C, and it seemed like a pretty significant uptick in difficulty. It looks like it's not hard in Rust. What do I know? Every year there's some students that work ahead. Those aren't like normal students, so we can't like measure them and see how hard things are, right? So like everyone that's done it so far said it was easy. Do we trust those people? No, they're nerds, right? It was easy for me. Does that help anything? No. Like, I think all kinds of weird things are easy. Like, I eat peanut butter sandwiches every day and think that's easy, and apparently other people think that's, like, psychotic, right? So anyways, I have no idea how hard this is going to be for you. I gave you 2 weeks because I think it's 2 weeks worth of difficulty. If you're done in 45 minutes, like, congratulations, I guess. Like, go take a walk. Like, I don't know. If you're all done in 45 minutes, let me know because I'll change it for next year. That's all. So you get 2 weeks on that. SHA-512 is a little bit harder than SHA-256, but is it really? So you're working with more bits, but you're actually just changing the number of times you run loops and things. So it's like the same number of characters of code, which is really odd for how much more complex it is. So that's kind of neat. Anyways, there is an intermediate checkpoint that is recommended but not required, and that's to get the bits into SHA and run SHA once. We cut up SHA into chunks of size 1024 and do one of the chunks this week, and then make sure everything else is working next week. Okay, why, what, how? These slides are stolen. I spent years trying to understand SHA, and I understood it for the first time when I thought this linked directly to the slides. This person made slides that I thought were really easy to follow, and I don't know where they are in here, but it's probably one of the, maybe this is a number theory and cryptography class. Does it say SHA on here somewhere? Maybe it's this one. Look at all this stuff that's going on. Look at that. We're transferring data. So this is what I'm teaching to you today, and I stole this, which I think is allowed. I did not actually originally learn SHA from this person. This person was the doctoral advisor of someone that became a professor in the United States, and I found that person's slides. So I actually had to do some tracking to get back to Saravanan Vijayakumaran at IIT Bombay. IIT Bombay is one of these schools where it's actually hard to tell how good it is. Because if you look at global rankings, the Indian universities are probably a little lower than they should be, but all the people that graduate from there, like, have ludicrous numbers of publications and stuff. So it is either a top 50 or top 5 university in the world. No one knows, right? Why? Hash functions. Y'all know what hash maps, hash tables, dictionaries are? Yeah. So we're going to motivate this that way. Basically, it's nice if you have a bunch of data to be able to take the data and make a number out of it. There's so many reasons to want to do this, but one of the easiest ones is like, I'd sure like to put these things in an array that's not as long as the number of possible files I could have, right? So we usually call this a hash signature. Now, in some languages that aren't cool, like Python, can I get some loud booing for Python? Thank you. Okay, so I think if I take a S and make it a set, and then I try and put that set in a dictionary as a key, so we'll make a dictionary, and I say like D S equals 7. That's not allowed because set is an unhashable type. That's fake. So that set is definitely some bits inside a computer. Why does Python not want me to hash that type? Well, that's not a mutable type. Or no, that is a mutable type. Is it a mutable type? Sets are mutable, right? I can add things to them. Right. So I can't have an unchanged hash for a set in Python. So Python doesn't let me hash the set. But for any data that's in storage in a computer, I can hash any file. Because the file is just a collection of bits, I can think of the file as just a number. That's fine, I'm allowed to do that. So we can hash anything stored in a computer. This is the special case where it's an interpreted language, okay? So, these things are also referred to by two other numbers, which are compression hashes and one-way hashes. Why is that? Well, if I hash something in Python like 1, I'll get back a relatively small number. But if I hash a large number, and we'll just take my favorite, I'm going to get back a much smaller hash than the size of the number. What that means, let's see. Is this going to work? So this value, 97 something, right, hashes to the same value as this number, but those are two different numbers, but they have the same hash function. This makes it one way. So what does that mean? Given this value, I cannot conclude what number, what file, what executable, what information was hashed in order to produce the output number. So hashing only goes in one direction. I can only make things smaller, and once something is hashed, I can't infer what the original data was. It's not about storing the original data. It's about measuring tampering to the original data. And we can see that because this will be a different value. And in Python, it's only different by 1, so this is not a particularly secure hash function, but it is, in fact, changing the hash when I change the number. And if I change any other aspects of the number, I will similarly get different hash values. Something interesting to notice about this example, I made that number much larger, and the hash value went down. So they're not related in terms of, I don't know, derivative or something, right? Okay. This is called compression, and one way for the same reason, which is that I take a large number of bits and I get a small number of bits, and specifically I get a fixed size number of bits. Is this a thing? So apparently hashes in Python are exactly 60 bits, and that's probably because 64-bit Python integers actually only have 60 bits of valid information, because they have 2 signed bits and 2 things called nails, which express whether the number has terminated or not at the end of its 32-bit chunk. So that is basically the useful integer size on my computer. And I think, like, no matter what I put in here. Oh, I got up to 61. Okay, so they're around 64, right? So these things are roughly the same size. Okay, how do we measure the goodness of a hash? Well, so say we take as given, and hopefully I've convinced you of this, the notion that we might want to have a one-way compression hash function. How do we tell it's good? Well, usually what you want to do is you want it to be unlikely that when I hash 2 different things, they hash or compress to the same value. And the reason I want to avoid that is I want to be able to tell if someone has tampered with my files that I've hashed, and I've stored the hash somewhere that's harder to tamper with. Or I want to push things in a hash table, and I don't want them to all go into the same cell of the hash table. These are both bad things. One of them causes a security problem, one of them causes a performance problem. Okay, so I want no 2 inputs to have the same digest or hash or compression or so on. The classic example is if you download Ubuntu. Who loves Ubuntu? Can I hear it for Ubuntu? Yay. It's just going to come up. Where's the hash values? Where are they? Hash? Signature? Okay, apparently there's no such thing as oh, wait, no. Maybe it's on Bionic Beaver? Where's the hash? Oh, there we go. Okay. How do I get rid of this? What is this thing? No, cancel. What? I probably don't want any of that, right? Okay. So, this is the operating system I'm using, or I don't know what version of Ubuntu I have. Here is a 2.3 gigabyte file. I think it makes sense to us that 2.3 gigabytes is a lot of gigabytes to make sure are all secure. That's a lot of gigabytes to pass over an Ethernet cable or over a Wi-Fi router, and many of them, it would be easy for them to get mixed up, right? Maybe I would want to download this multiple times to make sure I get it correctly. Maybe it would be very easy for someone to make ubuntu.con, and I would accidentally navigate to that website and download the wrong version of the operating system and give someone root access to my computer. So what do we do instead? Instead, someone takes this 2.3 gigabyte file and they compute the SHA. In this case, they use 256. They compute the SHA 256 sum of that file. This is a 256-bit integer expressed in hexadecimal, I think. That looks right. Okay. Now if I set this equal to x, length. So that is a 256-bit value. We don't have to think of it as an integer. It's not really an integer. Really, it's a collection of bits, but it's an ordered collection of bits, so we express it as a hexadecimal value. Okay? So, if I download some file, can I download a 2.3 gigabyte file in class? Will this ever finish? No, it will not. It's going fast. It's speeding up. So perhaps we'll be able to compute the hash of this in a minute.
The router is going to spin up first.
It's doing its best. Look, 4 minutes. Okay. So I download Ubuntu. I want to put Ubuntu on my computer. Before I put it on my computer, I want to make sure it's from someone I trust. And the person I trust is still on the other side of the internet. But it's much easier for them to get 256 bits to me that I trust than it is for them to get 2.3 gigabytes of information to me. So I take the 2.3 gigabytes, I will compute my own hash of that value, and I will compare the hash to see if it is the same thing they say it should be. And that is a way to measure it's been tampered with. Now, if someone has compromised the entire website, I'm cooked anyways, right? But this is still an independently useful thing. So, I want to be able to download Ubuntu and check its signature. And I also want to be confident that it is unlikely that if I downloaded, let's think of what is the worst program to have on your computer. So if I downloaded Internet Explorer instead by accident, right, I would want it to have a very different hash from Ubuntu because I wouldn't want to accidentally open Internet Explorer on my computer, right? So let's look at non-cryptographic hashes. It is assumed in this class that you are familiar with hash tables and hash maps, and if you're not, here are my slides on maps that hash. There is such thing as Python hash, and it's not very good for anything. Here is how I am going to describe a hashing function mathematically. It is my opinion that you should see this mathematically, so in case you ever go on Stack Overflow and someone has to explain this to you, they can actually just use the widely agreed upon notation. We're going to imagine a hash table, and we're going to say m is the size of some hash table. We're going to take a value a that is a natural number, so that is a positive integer. We're going to say it's not 0, but we're not going to comment on whether 0 is a natural number or not, right? Because we're not trying to start any fights. The natural number a is going to be less than m, and also co-prime with m. So this is the greatest common denominator of a and m is 1. Why do we want it to be co-prime? Well, I'm going to take a, and I'm going to be multiplying and dividing by a to change what number I am going to generate from my bits of information. And since I'm using a for that, I want to make sure that if I have, for example, a hash table of size 25 and a is 5, I will only be able to generate multiples of 5, so I will not be able to use every cell in my hash table. If two numbers are co-prime, that means when I take the multiples of one number, so if I take any number times a, and then I take it modulo m, mod m, I will be able to use all of the cells of the hash table because I will sort of iteratively walk over the cells before looping back to the beginning because I will hit every value for m. Let's look at an example of this. So what is a number that is co-prime with 25? I think 3, right? So we're going to multiply 3 times I and take it mod 25. And this is all of the values up to 25, but it is in an arbitrary order. One way to verify that we can be highly confident that this is all of the values up to 25 is we can reformat this as a list comp. It's very hard to type and think about hashing at the same time, I've noticed. Okay. Oop, yep, I'm typing just the wrong numbers by accident. So these are the values I just looked at. I say sorted, right? And we can verify this has coverage over all of the values we would expect by taking them and putting them in a different order. But if I hash something within this range, it's unclear which one of these values I'm going to hit. And so if I also do this, not over range 25, but over, for example, what are 2 numbers that are 25 apart? We'll do 137 and 137 plus 25, which I'm not going to try and do mental math. No, I am. Okay. 5 to 62? Yeah? Okay. So that's the usefulness of this hashing algorithm, right? I am unlikely to get the same number, or I am exactly as likely to get the same hash value as I am the number of cells in the hash table. Okay. We can express this in a programming language. I don't know. We kind of did this already. It just so happens, by the way, that 257 is prime, which is, maybe that's useful to you. You can do this a lot faster if you are able to use the shift operation. I think this is how you do that in Rust. I'm not sure. But here is an accelerated version. You can try this out on your own. People have put a lot of word and effort into making hashing very fast. This is also our second reference this class to words. So I mentioned in x86 assembly, word is the name of 16 bits of information, double word is the name of 32 bits of information, and quad word is the name of 64 bits of information. So we have this notion of word size. Rust by default uses 32-bit words because it uses I32s. So if you're storing words, or if you're storing things based on an address that is a word, that's what your word is. Now, more properly in Rust than I32, I think these should be U sizes because they're addresses of things we're storing in memory. And Rust U size is the address size. That's AI, so we don't trust that. Right. Do you trust AI?
No.
Maybe you should. Yeah, this is for how big information is. Okay. So this is an accelerated high-performance hash. This is not a secure hash. This is an accelerated high-performance hash. Okay. The thing we want to look out for is collisions. The collision is when two things collide, and I have expressed this mathematically as follows. There exists x and x prime such that x does not equal x prime, but the hash of x equals the hash of x prime. We can do one example of that with our hashing function we've introduced here. Hash equals lambda of x is 3 times x mod 25. And we can see that that is the same. Ooh, that's probably not correct then. What did I do? Why is it all 10?
Maybe maybe Python's hash just really sucks.
Yeah, is it referring to... How is that? Does anyone know how Python works?
Is there a built-in hash function?
There is, but I replaced it. I namespace collided it. I clobbered it, as they say. Can you believe clobber is a real word that people use in real life? That sounds like a made-up word, right? Okay. I really would not have thought that would happen. But, like, there is... Wait, what? Did I spell hash? Oh, I said hash X. See that? Instead of I. And so what do we do when we make that kind of mistake? You go...
Write it on a shirt.
You go honk honk because you're a silly goose. Honk honk. Okay, all right. That was fun. Okay, so we can verify that these things are the same. So let's construct a hash collision. I can take the hash of 7, and I can take the hash of presumably 32 and get the same value. So it is possible for there to be two different x values that have the same hash value. And I showed you this previously with the built-in Python hash, which I don't actually know how to get that back. Where I said hash of... That's too small. Oh, right, because I meant to do power. So this value hashes to that value, but also this value will hash to itself, I think. So it is the case that these two values have the same hash function and the two values differ. And that is the case of a hash collision. I expressed that in Python, and it's the same concept I'm expressing here. Here's another assert statement in Python referring to the earlier hash function. Oh, this could be Rust. It's not Rust, right? Because there's not multiple assignment in Rust. Oh, and there's and. Okay, so what is bad about collisions? In a non-cryptographic context, collisions cause you to have worse performance in a hash table because you have hash collisions, and so whatever you're doing to avoid hash collisions, you're no longer getting constant time lookup, right? If you're using double hashing, you're still paying some cost. If you're throwing a linked list in those hash cells, you're paying order n, right? So you want to avoid having collisions in a non-cryptographic context for performance reasons. Now, in a cryptographic context, it is much more vital because the reason you're trying to avoid collisions is so people aren't accidentally imaging their computer with malware. And at this point in time, I think we should probably assume that we finished downloading this file, and we should go see that if we got the correct hash for it. So let's see if we can do that. Wait, where's downloads? Okay, so I have Ubuntu there, and I can 256 some Ubuntu, and that will probably take some time. And then we will come find, was it in my history? Did I get the, okay, so Ubuntu has reported to me that I should get something that starts with F730, and it's the same as this. Now, something that apparently is common in hash attacks as well is it is much easier to get a different hash that looks the same. So if you combine, for example, the 4 leading and following characters, you might want to do that. So an obvious thing you should do is you should take the diff of both of these, right? So I should take this and throw it in my file system. Ref.txt. And then I want to take, well, let's diff ref and, okay, I'm just going to copy this too. there's a good way to do this, and I am too tired to figure out what it is right now. And so there's no difference between those two hashes, so I can be highly confident that I downloaded the version of Ubuntu that I thought I did. Now, how do we avoid having collisions? This is an exact quote from Saravan at IIT Bombay. Achieve collision avoidance with a large codomain for H. So what is the large codomain for H? It's also called, and I think this is easier to understand, the set of destination. This is the set of possible hash values, right? So the thing that's causing the collisions in Python in the example I've shown you is I only have around 60 bits of precision, and I'm hashing much larger numbers than that. There are many more numbers that are bigger than 2 to the 64th than smaller to 2 to the 64th. So I'm just going to run things into each other. The same thing is true with files. This file is very small. It is 65 bytes in size. That is much smaller than the 2.3 gigabytes that I generated that value from, right? So I have a small set of destination, which is 64 bytes of information, which is 256 bits of information. I have a much smaller set of destination than I do set of inputs, right? So when I have a function that goes from X, which is all possible files, to Y, which is files that are 64 bytes or smaller, I'm going to lose a lot of information. The term range is also sometimes used for this. I'm using term codomain because I think it's correct. Are there any mathematicians in this class? Did someone raise a hand?
Class, and that's what we use.
You used codomain?
Yeah.
Okay.
Codomain.
So I think codomain is consistent, at least at this university. Okay. As a rule, you shouldn't write proofs in Python, so I didn't. I tried to write a proof last year, and it melted my computer. Okay. Here's a visualization. We take a series of inputs. We place them inside our hash function. So this is Ubuntu. This is Gentoo. This is Fedora. We don't have Arch or Nix because we don't use those. We put it inside our hashing function. The hash is generated. There are many bins that each thing could fall into, and we can think of this as hash tables or not. When I hash something, perhaps it hashes to 0, or perhaps it hashes to 2, or perhaps it hashes to 2 to the 256 minus 1, which is the maximum value of a 256-bit sized hash, right? So this is how I think of this. Given some file, I figure out what bin it goes into. That bin has a number on it. That number is the hash value. You can think of it other ways. Okay, so that's what we're trying to do. Does anyone want to ask me any questions about anything? I don't expect you to want to ask questions, but you can if you want. I can also answer questions about things unrelated to this class if they're within my areas of expertise. Okay. Does anyone want to ask me anything about vector operations in NumPy? I've been thinking about them a lot lately. Okay. They seem so cool, you know, right? Like, of course I want to be able to multiply an integer by a vector. That's awesome. Okay. So we're going to begin with Secure Hash Algorithm 2. It is a family of cryptographic hash functions. It is not a cryptographic hash functions. It was published by NIST in 2001, but I think it was developed by the NSA, which is maybe the National Security Administration. Yeah, National Security Agency. There you go. SHA-1 was released in 1995, and it was bad. It is relatively impressive, actually, that a hashing development that replaced something after 6 years is still around after 24 years. There are ongoing research efforts to try and generate collisions reliably with SHA-2, and it's just not working. It still seems very secure. There is also an SHA-3 which has not been deployed yet, but it does exist. And so the reason for that is SHA-2 is so important mainly to global financial security, because this is used to sign bank transactions. It's basically so important that if a weakness were revealed in it, it would have to be fixed probably by the close of business day, or $1 trillion would disappear or something, right? So SHA-3 already exists and is already deployed and also has no known weaknesses. So they are both regarded as secure right now, and SHA-2 is the one that is in use. I don't know a lot about SHA-3. My understanding is the reason SHA-2 is still in use and going to continue to be used is, first of all, This thing doesn't look like it's remotely ever going to be breached to me. Like, it seems totally fine. And also, it's wicked fast. It's been around for 24 years, so people have gotten very, very good at doing it very quickly. And this ties back to the earlier discussion we had where I said, my computer can just rotate bits. It can just do that. It didn't have to do that. There's no reason it has to do that, but it can do that now because SHA has been around for 24 years. And people were rotating bits so many times, the computers can just do it as they can and add. And that was not true when it came out. These 6 hash functions were released August 2001. And I have only ever seen use for these two. Those are the ones with powers of 2. These are like shorter or something. I don't know who uses them. I mostly see 256 used. We're going to use 512 for something later this term. Sometimes you just need more bits. But realistically, 2 to the 256 is an enormous number. Like, there are not that many files. So I think we're okay. The 2 things I'm going to point out to you that this has been used for in practice, and when I taught SHA last time, it was in a Bitcoin class, so it's used in Bitcoin. I don't know if you care. 512 is not used in Bitcoin. 256 is used in Bitcoin. Both 512 and 256 are used in digital signatures, which is the example I just showed you with Ubuntu, and they're used in version control systems. So Git uses these. Git might be moving around big files much larger than 64 bytes in size. When you're moving around files of that size and you're trying to keep track of them and make sure there's a sort of historical record for how those files came to be generated, it's important to be able to verify. So in addition to GitHub, or Git, more properly, not GitHub, Git keeping track of changes to your files, it also digitally signs them. And so this is used in a version control system. Yeah, and then other stuff is blockchain. Okay. We are now at the point in this class where I'm going to teach you something that is actually used in real life. And I'm going to ask you to write your own version of it, and your own version of it is going to not be secure. And it's not going to be secure for a reason that is very, very hard to teach. Okay? So, we are going to ask you to take the SHA pledge, and I am going to require you to repeat after me. Where's the pledge? Okay. Okay, I'm just going to tell you what to say. Okay, raise whichever hand is your preference. I'm going to use my right hand because my left arm is tired. And say, I will never use any code I have written in this class for anything.
I will never use any code I've written in this class for anything.
The code I write in this class is dangerous and should not be trusted.
The code I write in this class is dangerous and should not be trusted.
I should use code that people that know things wrote.
I should use code that people that know things wrote.
I do not know things.
I do not know things.
Professor Calvin does not know things.
Professor Calvin does not know things.
We don't even know who knows things.
We don't even know who knows things.
All right, thank you. Okay. So it is true that last term I wrote this and then I changed all of my GitHub keys to things that I generated myself, and that was probably a really bad idea. So I didn't follow the pledge. Okay. SHA 512 overview. What's the 512 stand for? It stands for how big the output size is. I showed you SHA 256 sums, and I said, oh, look, it's a file of size 64. Those were 64, or 65. That was 65 characters and an end-of-file character. So 64. 64 of those that each hold 8 bits of information. 8 times 64 is 256. If I compute the SHA 512 sum of an SHA 256 sum, because that was the file I happen to have, it will be twice as large. So this thing contains 512 bits of information, and that is expressed in so this is 4 bits per character. SHA 512 accepts bit strings. Why do I say bit strings? What else am I going to say? I don't really want to say files every time because they don't have to be files. It can be concatenations of files. It can be other forms of information. It can be executables, which are not necessarily a file, right? It can accept bit strings of length up to 2 to the 128 minus 1 bits, not bytes. So that is 340 undecillion bits. How do I think of the term undecillion? So million, the M in million, I guess, is taken to refer to as mono. So billion is by 2. So if we think of million as 1, billion as 2, this is 11. So this is a 1 followed by 11 times 3 zeros plus another 1,000, because for some reason we start counting million, which is 1,000 thousands, right? So this is a 340, comma, 12 sets of 3 zeros. And septillion is similar, so that is 7, so we add 1 to the 7 because we have an off by 1 error. So this is a 42 followed by 8 sets of 3 zeros, terabytes. And I think of the terabyte as the size of your hard drive. So that many of your hard drives. My understanding is this many bits don't exist, but you never really want to make claims about how many bits there are with how fast data centers are growing right now. So if Google's just been like deep faking millions of hours of video footage in like 4K Ultra HD 120 FPS, they did hit this number, I guess, probably. Because there's only so many zeros, right? But I don't know how they'd store all of that, right?
Yeah, I'd be concerned about storage space.
I'd be concerned about storage space. But they nominally have, I mean, on the order of millions or billions of drives that store on the order of thousands or millions of terabytes. And so when you add that up, it's like, yeah, we're within like 7 orders of magnitude, right? I don't want to round across that. How? So a lot of people don't know this, but SHA is actually super easy. There's only pre-processing and hash computation. So, did it not fit on one screen? Oh, it didn't fit on one screen because I made these slides with the smaller... so I was used to having the 32-bit values on here. Here, let's see if I can zoom this out.
It's on my screen.
It fits on your screen? Works on my PC. Okay. Are you on Windows?
Yeah.
Okay. Can you show me your screen so I know what it looks like? Oh yeah, that's what it looked like on my home screen where I also use Windows. Okay. Do you have this indentation here? Okay, so that's an error in the source code. This other thing is error in portability. Okay. So, before you do anything related to SHA 512, what you're going to need some initial values. This leads to this really quick chicken and the egg problem where it's like, why do I need the initial values? Well, we need the initial values because we're going to use them later in the algorithm, but we need to already have them by the time we use them, right? So I often think of this as one of the first things you do. There's going to be a 512-bit state variable, which we usually refer to as H, and this is H superscript 0. And then I break this out into words, so this is 0 through 7 words, so that's 8 words of size 64 bits, and 8 times 64 is 512. So this represents 512 bits of information. What are these? These are the fractional parts of the square roots of the first primes. What does that mean? We're going to get a lab on it, but it's not that bad. Can I do this in Python? I think. So if I take 2, and I take the square root of 2, and I take the fractional component of the square root of 2, that's 0.414. And if I want to express that as a 64-bit value, I'll multiply that by 2 to the 64. And then I think I can just take the hexadecimal representation of that, but I have to cast it back to an integer first. Does this seem right? And so that value is 6A09, 6A09, E667, E667, FCBC, FCBC. And then I have rounding errors here because I run out of precision in Python. So these last values have to be calculated through some other means than using sort of the built-in Python type of numbers. But if I take this value, divide it by 2 to the power of 64, add 1 to it, and square it, I will get 2 back. And the same thing is true with this value. This will become 3. So there's BB. What's the third prime number? Is it 5? Oh, I'm not subtracting the 1 off. Oh, no, I have to subtract 2 off because 5 is bigger than... Okay, there we go. 3C. And then the next prime is 7. Do you all know what prime numbers are? 5, 5, 4. A5, 4. Okay. So that's how these values are generated. You can generate them yourself. And in fact, I think if you're in luck... That's... Nope. I'm telling lies. Don't listen to me. What? Why did I do 2 slash... Okay. Here we go. You're in luck because actually, I was going to make you do that this week. I need to update the calendar. But I'm just going to make you generate these constants. Isn't that fun? None of you are actually... Can I hear, like, some joyous sounds? Like, woo! No? Okay. All right. Well, I did this myself, and I thought I had a good time doing it. Okay. So I have my initial values, and I'm setting my initial values to one side. I can think of this as I'm defining variables at the beginning of writing some function, right? Okay. Then I'm going to take the input m. Usually use m to refer to message, if we're thinking of this as a message passing over the internet. Okay. Now, SHA 512 can only work with things in chunks of size 1024 bits. And not everything is of size 1024 bits. I know you don't believe me. That's okay. I'm going to demonstrate this to you. This is a file, and it is not of size 1024 bits. Okay, it is smaller, right? So however big your file is, and I think... Ooh, it's going to take some time. Okay, gigabytes are big. If I have something under 1024 bytes, what I'm going to do is I'm going to pad it. So I'm going to add bits to the end. And the way you do this... I wonder if that's supposed to say 1024. I'm going to find a value. And that value is going to be how many bits I need to add on to the end of this thing to get up to a multiple of 1024. But I'm not going to add on that many bits. I'm going to add on 129 fewer than that many bits. Because I'm going to use one of those bits to denote the end of the message. So I'm going to put a single 1 bit, and then I'm going to put a large number of 0 bits. And at the end of those large number of 0 bits, and that's the k0 bits, I'm going to put the binary representation of the length of the original value as a 128-bit integer. That 128-bit integer was the original maximum size for how much I could hash. So, when I take, for example, wait, what am I doing? Okay, we're done with that. Hex dump ref.text. So, this is the hexadecimal representation of ref.text. If I were to start padding this, I would go to this block here, which is absent, and I would do a 1 followed by a large number of zeros. So I would place a single 1 value here. Now, it gets really confusing what placing a single 1 value means with endianness, which is the way we represent our values in memory, right? So somehow you have to put a 1 at the end of that. So usually that actually looks like a 2 to the 64. So probably this will be, it'll be 80000, right? I'm not gonna use Python to figure out what the hex representation of 1000 is. It's just 8, right? Okay, fine. Bin OX8. Yes, okay, I was correct. Why are you all messing with me? Okay, that's fine. I still respect you all. Okay, so there'll be an 8 here, and then there'll be a bunch of zeros, and there will be zeros until I get up to the 1024-bit boundary, and then the last 128 bits, which is, how many of these? It's like an entire row, because I think that's 8. That will be an 128-bit integer that says the size of the original payload, which in this case is 65 times 8, which is whatever, I don't know, something easy, right? So I'll have 520 represented, and it will be represented in either hex or binary, however you want to think of it. So you will have, again, a large number of zeros, so there'll be an 8, many zeros, until we get to the 1024-bit boundary, and then the last 3 or 4, however you want to think of it, bytes will be 208 to represent the size. representing the size is really useful because even if you get a size collision, or even if you get a hash collision, it's unlikely to be the exact same size. So all of the examples I showed you of hash collisions in Python, I was using different sized values, right? That made things a lot easier on me. So this is going to protect you a little bit. This term, this thing here is congruence. So this is congruence modulo. I'm 100% sure that's supposed to be 1024. I will check. I've been wrong on this before. We take some value, we figure out the value. We know what L is. It's 208. We know we need these 129 bits because I need one bit that has to be a 1 and 128 bits that store value. And that has to equal 0 because it has to be some multiple of 1024 or 512. Gosh, I wish I knew for sure which one it was. I will check this and update it. I don't think it matters. Okay, so we're going to add the padding content. So we're going to take k plus 129 bits, this k that we just found. We're going to add them to the end of that m. We place the 1, we place many zeros, and then we place the 128-bit representation. So I have a 1, many zeros, 128-bit 8-bit representation of length. So many of these 128 bits will themselves be 0, right? But they will have a different meaning. You can solve this numerically with Python. This is what it looks like. There's a lot of zeros, okay? I don't know how many zeros that is, but I think the scientific term for this is a whole bunch. There's a whole bunch of zeros there, okay? And I did this, I used this technique known as cheating, where I just use string representation here. So it's relatively difficult to get this to work numerically. You can work on that if you would like. But writing the padding operation is interesting. Okay, so I'm going to compute my hash. I'm going to pad input that is split into n, yn, because we don't know how big the input is going to be. It's in between 1 and however many you can fit in the maximum size. So we're going to take n 1024-bit blocks. It's SHA-512, but our block size is 1024. And I'm going to note that this is 1-indexed. So when I break up my message, I'm going to 1-index it, and there's a reason for that. We're going to see what the 0 index is later, okay? So I'm going to have M1, M2, MN. In your first week, this week, you only need to deal with M1, but, write good code. This was hard for me to test because you have to precisely type in 1024 bits and recognize them and tell if they're in the correct order and stuff. So I did a lot of this thing that you've seen me do where I'm like, oh, A, B, C, D, 0, 0, 0, 0, 1, 2, 3, 4. And it's like, oh, I can recognize that if it shows up in a hex dump, right? So that's a lot of bit. You might want to just write a file that has some bits in it and test it with the same file every time, okay? And then go over the 1024-bit boundary once you know it works. And of course, you can use the complete text of Pride and Prejudice or whatever you want to use, right? My claim is that you know how to do this already. Okay, here is the type of our hash function. We are going to take a message, and this is a message chunk that is represented in binary of size 10 to 24. So I am not saying this is an integer, right? I'm saying this is an ordered collection of bits. Then we're also going to take some h value. This is sort of our initial offset. That is going to be of size 512, and this is going to produce an h prime, which is also of size 512. So I take 1024 bits of information, 512 bits of hash, and I get out 512 bits of hash. And then given some previous h value, we're going to use the previous h value and the current message value to get the current hash value. And we do this for all n. So I'm going to do this many times. I'm going to cut off 1024 bits of my file. I'm going to take what my current hash value is. I'm going to shuffle them up, and then I'm going to get 512 bits out. And then I'm going to take those 512 bits, and I'm going to take the next 1024 bits from my file, and then I'm going to move on. I'm going to do this repeatedly. So this is a loop, but it's a 1-indexed loop. This is probably what you want to do. Oh, hey, it's a C comment. That's fake. This stuff was supposed to get cut out, and it survived somehow. So here's the type of my rotate function. I think, okay, if someone's in Discord right now, I think this is an error, and I need to check that that mod 512 is an error. I'm pretty sure it is, but I need to look at like a lot of things to be sure. So someone Discord me or something. Okay. We're now just going to review the bitwise logical operations and how we compose them. How many minutes do we have left in this class? 35? Okay. How's everyone doing? Do we need to do like a monkey type and or stretch break? You want to grind. Okay. Dig deep, grind hard. That's what I say. Okay. There are a series of different bitwise logical operations: unary, binary, and ternary. You haven't ternary? Someone say this. We do think ternary? Okay. And then there's shift and rotate operations that can either be simple or composite. Okay. So, there are bitwise logical operations that accept 1, 2, or 3 words. I'm saying they're of size 64. Really, as defined, they work over any word size. So if you have a word size of 7 bits, or even 6 bits, which was possible in the ancient past, that was true. And so I'm going to take 1, 2, or 3 words, and I'm going to output a single word. I term the words UVW. Do not overthink this. This is W. Why did I not say WXY? Because we used X and Y for everything. So I just went backwards from W. So UVW are the names of my 3 words. Shift rotate operations are going to accept 1 word of any size, and they're going to accept 1 natural number that is smaller than the number of bits in the size. So this is kind of weird. You would represent this actually as a U6, which is not a thing that exists, right? So I'm just going to say it's going to be a small natural number, and we're going to turn this n, and I'm using lowercase italics n. It is not a word. It is something else. It is just a number, and it is meaningful as a number. These bitwise operations working over words, we do not care if these words are integers or thought of them or something else. They're just information. But this n is very specifically a number, and it is meaningful as a number. So you already know the unary bitwise operation. There's only one of them that's famous. Bitwise complement, bitwise logical not, always expressed this way. Oh my gosh, these slides got destroyed. What happened here? This is supposed to be a section break. This is from the bits lecture, okay, which is the encoding lecture. Imagine there's a slide, so pretend I'm going to the next slide. Okay, we're on the next slide. Okay, binary bitwise, there are the just 3 famous operations because we don't use not and, right? There's no built-in NAND on my computer. NAND is actually very interesting in digital logic because it's quite fast, so it's used a lot in practice, but it melts people's brains so we don't think of it, right? But it's just the negation of and. It's nothing special. We can compose it from these ones. I'm adopting the convention. I learned these conventions in math class. I don't know what you use, but this is logical and, bitwise and over words, right? Bitwise or, and I think that's conjunction or disjunction. And then we also have XOR. So I'm using this sort of like, I don't know, window. It reminds me of stained glass. I don't know what you think that is. I'm using that to represent XOR. XOR is very common and very useful. Why is that? When I AND 2 things together, I reduce the number of ones. If I take 2 random bit strings, I expect them to have n over 2 bits set to 1. If I AND them together, I expect them to have n over 4 bits set to 1. So I'm pushing things towards having 0 bits. If I do OR, I start with 2 things that I expect to have n over 2, and I expect to have 3n over 4 when I get that back. That's sort of the expected number of bits. So I tend towards having many 1s. I could, if I were a brain genius, combine a combination of ands and ors to get the expected number of 1s and 0s to stay the same. That's a lot of work. So by convention, usually when we're messing with bits and we're trying to do cryptographic hashing, we use XOR a lot, because if I take 2 values and I XOR them, well, basically, I'm going to keep the same number of 1s. I'm just going to change the arrangement. We are also going to make the claim that addition is basically a binary bitwise operation, which is not too bad. You can think of it as integer modulo sum 2 to the 64, and this is really hard to show. From C types import C U long long. I think I can take, so that clips right at 2 to the 64. And we can think of there as being a binary bitwise operation where like I add two of these things together. And it, okay, I'm not allowed to add those together. Why can I not add long longs together? I don't even have that. Okay, I did not expect it was going to say it was a different type. Okay, so what's going on here, and I don't know a great way to show this, so I'm just like hacking in Python so we can look at it. Long, long, this long is referring to a long word. Words are the 16-bit type, a long word is the 32-bit type, a long, long is longer than the 32-bit type, so that long, long is the quad word, it is the 64-bit type. Okay, so this is a way to refer to an unsigned 64-bit value in Python, to my knowledge. Is the better way to do this np uint, what are they? Is this allowed? Yeah, so somehow you want roughly this value, right? 64 bits of information. We can think of additions over this 64 bits of information as just a bitwise operation. And here's one way to do that. We'll do x. So we can look at that value. We can look at this value, and if we add those values together, was it 2 to 63? Why can I not type? Okay. Maybe we understand that as some bitwise operation. Maybe this is better if we do like 60. And we look at what each of these two things look like individually. Right? So maybe we can see that we're adding the 1 to the 8, and that looks an awful lot like an XOR. And I think I get the same value in this case with XOR, so it behaves a lot like a bitwise operation. Now, one of the problems with integers, and I actually haven't been able to figure out this probability manually myself, is with addition you have carry bits, so I'd assume you would tend towards having more ones over time, but you also clip the top bits, so maybe you don't. So I can't tell if addition changes the expected distribution of ones and zeros within a bit. If you figure out a good way to express that mathematically, let me know. That's like an extra credit problem. But I think it's very close to not changing the distribution. It's just not as easy as XOR. This is heinous and awful, as you probably noticed. I'm making a claim. I'm giving Rust 1 gold star for just naming its integer type something that makes sense. Like a U64, you know what it is and how big it is. It has nothing, you never say unsigned long long and like have to go through the history of computing to explain what a long long is, right? So Rust is new and good, okay. Rust addition on U64 is already modulo 264. Let's check it. Wait, why am I here? Temp cd rot ls nvim circmain okay. Right. So I'm not allowed to add these two numbers together because it causes an integer overflow. Why is that? This value, and I don't think it's particularly easy to see how big it is the same size as this value, which was 1 less than our overflow size on the 64-bit integer in Python. So I can't add those two things together, which means that I have only a finite number of values. Okay, this is banned. My bin was called bits. Okay, I'm going to say at this point you understand the unary, which is complement or negation, and the binary, which is OR and XOR and maybe addition operations. And I'm going to introduce two things that you probably haven't seen before because I've only ever seen them in this context, which is choice and median. Y'all have seen choice and median from the macros assignment, right? You have some sense for what they are. Choice means you look at the first of 3 words, and if the first of 3 words has some bit, you use that bit as sort of the index for the later words. So if the first word, then the second word, not other. So you can express this. This is one way to express that logically, and this is a implication translated into a combination of nots and conjunctions, right? So if you, then the, else kind of, right? XOR, because we're just taking the other bits. If not you, then we also take W. Okay. And it's helpful, we can XOR these things because these two are logically exclusive, right? This could also be an addition, it doesn't matter in this case. Median I thought was super cool, and median also helpfully scales to more than 3 words, right? But it only works on odd numbered words, right? So this is if any 2 bits are set, then median is true, right? So the median is sort of the most popular of the bits from the 3 words. Why are these useful? Well, if I need to take 3 different words and combine them such that changing any one of the bits in any one of the words changes the output value at high probability, in this case at 50% probability, right? Then I can use any one of these and I can combine things 3 ways. This is going to have a different distribution of outcomes than like doing XOR twice or something, right? So it's pretty useful. I stole these from Beacon, who implemented a bunch of the algorithms. And this is like old legacy holdover from doing this in C, but logically it's identical. Where is it? There you go. Here's choice, and here's majority. And majority and median are the same thing, right? Okay. Shifts and rotates. Wait, no. Are there any questions about choice and median? You're already working with them, right? Is macros assignment going okay? Are you all done? Okay. Is anyone stuck? Okay. If you are stuck, let me know. I would like you to not be stuck on that. And I think it makes sense, but if it doesn't make sense, we should figure it out. Okay. Shifts and rotates are weird. And they are weird because they accept 2 different types. One of them is an information type, and one of them is a numeric type. And we express them both as bits in computers. So we're going to cap our numeric type at size 63, or at value 63, which is not really an easy thing to do in a computer, because that's 6 bits of information. Whoa, what's going on here? Do your screens look like this? I checked these slides like a couple days ago. That's so sad. Okay. Dang. Does it look okay on your Windows device?
No,
It just looks awful?
it's evil. It's about as evil and messed up as it is on yours.
You can see there's something here, right?
Yeah.
Like that's supposed to be LaTeX.
Yeah, it does not show up on the projector at all.
Well, it shows up when I highlight
Yeah,
it.
when you highlight it.
Yeah. I wonder what broke. Okay. Oh, I don't want to stand up. So my feet hurt. Okay. I think I sprained my ankle. As in, like, the search and rescue team member that heard the noise I made said that's the sound people usually make when they sprain their ankle, which is a hilarious way to be diagnosed, right? Okay. So shifts are easy. I can shift this to the right. And if I shift it to the right by 2, I simply take all of these values and move them over 2 places. So it goes like this. 0, 0, 0, 0, 0, 1. What happens to these places? Well, usually the 2 high order bits that are left here for imagining this as a single byte shift is, well, actually, you specify when you're telling the computer what type of shift you want to perform. In practice, usually it's assumed you just take the same one. And why do you do that? Well, if I threw a negative something in here, so I think like this is negative 16. I don't know why I trust Python. Oh, it's just going to throw a negative value on the binary, isn't it? Yeah, that's useless. Okay. Python, bad language. Okay. So, if you take a negative 16 and you bit shift it by 2, probably what that means is you wanted to divide it by 4, because this thing is divided by 4. That's 7 divided by 4, giving 1, which is about makes sense mathematically, right? And if I had a 1 here and zeros here, then I would have a 1 here and zeros here. And that would be 16, blah, blah, blah. Okay, so if you shift like this, you probably want to populate these with 1s. So you want 0, 0, 1, 1, 1, 1. Now, if I take this and I throw zeros here, this is going to be 4 plus 8 plus 16 plus 32, which is some number, 61. Is that right? No, it's 60, right? Because it's even. Is it 58?
60.
It's 60? Okay, thank you. How did you check?
I opened a Chrome tab and added them.
Okay, cool. And you probably don't mean to take negative 16, divide by 4, and get 60, right? So probably what you want here, and I say probably because, like, who knows why you're using a shift in a computer, right? No one knows. You know, maybe you don't know, right? You probably want 1s here, and if I throw these 1s in here, then this whole thing is going to look like a negative value, because it's all 1 preceded, and so this is going to be negative 3, which is about a quarter of negative 15 or something, right? So that's roughly going to make sense. So this SHR I have here, shift right, I'm treating that as if you add zeros to the beginning, but you don't necessarily want to do that. So you just add more zeros at the beginning, and then these indexes go over. So this is where I say U0, this is U0, so this becomes U0, and then this becomes the N zeros. So I don't know how to do italics N. So I'm going to do underscore, that is an N, not an H, another underscore, and then I'm going to say zeros, right? Rotate is basically the same. The only difference, I'm just going to do vertical lines for 1s, and we're just going to understand what I'm doing, okay, right? Because, like, writing those was crushing me, right? Okay, so if we do a rotate, we do the same thing. These go over to here. But these ones loop around. And there's no graceful way to see that. So we get 1, 1, 0, 0, 0, 0, 1, 1. When you use this, never accept an SHA, as far as I know. Some things to think about. I've mentioned you might be invested in conserving the same number of 1s and zeros because you don't want to, like, every hash of a large file to only be zeros and every hash of a small file to only be 1s or something. This shift operation preserves the number of 1s and zeros. Or no, this rotate. Rotate preserves the number of 1s and zeros. Shift does not. So, when you're doing cryptography, rotate's probably looking a lot better to you. When you're doing, like, math, you're probably using shifts all the time because you're mostly doing divides and multiplies. So they have different use cases, right? But the rotate conserves the number of zeros and 1s. Now I'll try and figure out what's wrong with these slides at some point. And one of you remind me if you can. Since I had to do that on the board, it's not going to be captured as well on the recording. Does anyone want to ask me something about this so I can say something so I remember what it looks like? And I'll try and fix the slides. I want to preserve the number of ones and zeros. I want to change the order of the ones and zeros. That's all. SHA is best expressed in terms of these things that I've started calling composites. I don't know what other people call them. This is big sigma, this is little sigma, and there are 0 and 1 subscripted big and little sigmas, and these are combinations of right rotates XORed together with other right rotates over one operation. So these sigma values join logical negation as being unary bitwise operations because I apply this to a single value, right? So you can use macros and helper functions that work well here. Okay, hash computation. I'm going to do 4 steps. On the first chunk, I'm going to take my pre-computed H values and my message, and I'm going to throw them into some loop. That loop is going to use pre-computed K values, which are the cube roots of the first n prime, so they're just numbers that are generated procedurally. And I'm going to use these in each round. So I'm going to have chunks and rounds is how I call it. So we're going to pre-process. We're going to set something called the message schedule array, which has 80 working variables and 8 word size variables.
That's 80 working.
I don't believe you. I don't see the word orking there. Okay. These slides were so good. I don't know what happened to them. I was very tired when I worked on them last, so I have a pretty good idea who sabotaged these. But in my defense, my plane got in late last night, so that's what we're blaming for this. Okay. Then you do the main loop, which is word level operations, and then you update the hash value. Okay. So how do we set the message schedule array? I have a big thing of many 64-bit words. Specifically, I have 80 64-bit words. The first 16 64-bit words come from the 1024-bit message chunk. 8 times 64 is 1024. The next 16 through 80, which is 64-bit words, are populated by applying little sigma to the 2 prior words, taking the 7th prior word, applying another little sigma to the 15 prior word, and adding the 16 prior words. So what is this? I look at 4 previous words, and 2 of them I perform unary bitwise operations on, and then I put that at that position in the message schedule array. So I think of this in terms of message scheduling as you have to successively populate this array because it refers to prior values, and we seed the first 16 with the message. So these values are always defined. So when I calculate W16, I can look at J minus 16 because that's 0, because that's the first chunk of my message. And so I can populate 80 by 64 bits and have a big chunk of information. Then I'm going to set the working variables. This is just going to take the previous hash values. So I'm going to take 8 of them, and by convention they're referred to as A, B, C, D, E, F, G, H, and the problem with that is H is used in a bunch of places, right? So you will have namespace collisions when writing this. I solved this by not naming any of these variables and using an array. You can do whatever you want. Then you are going to iterate. And you're going to iterate with variable reassignment. The way I did this, are we out of time? Do we need to go?
Yeah.
All right. I'll finish this next time, whenever that is. I see you Wednesday. See you Wednesday. Have a great day. Maybe I'll be able to stand up by then. At Pikes Peak. Oh, I was so close. I was like within 5 minutes of finishing on time. Like,
You went early last time, now you're too late.
Maybe we needed those 5 minutes at the start.
Yeah, that Wordle.
Yeah, the
Yeah, the Wordle really grew.
Yeah.
The Wordle.
I'm so sad. I was like looking at the clock the whole time. I'm like, I'm so close, right? And I bet if the slides didn't break, I would have been okay too.
I take the class because I know. No, I